All right, what I want to do with you guys really quick is go over just the basic intro stuff for logarithms on this magical half day so that we can get some kind of understanding before we continue to move forward in what is, according to some people, the most complicated and confusing unit that you will deal with this year. If you kind of get a hang of the basics before anything else, you should be a-okay. But I want to make sure that we get those basics down and just very briefly go over a couple of key things before we get more in depth tomorrow. First things first, let's talk. The word logarithm is absolutely atrocious. And if you know anything about mathematicians, we love to be lazy and make things as easy as possible. So instead of saying logarithm all the time, you can just say log, and that is totally fine. On your calculators, you will mostly find a log button as you are to deal with any of these things rather than a logarithm button. Now, you should have access to this exact little web worksheet. So I have this piece for you here. I will just show it so that you guys can fill in along the way. A logarithm is just a special way to ask a very specific question in math. Logarithms, the basic of a logarithm looks a little bit something like this. When you see this statement here and it says log with a small b at the bottom, a equals x, you read that as log base b of a is equal to x or is x. So that's log base b, base at the bottom, of a is equal to x. That very specific question that we talked about when you are dealing with a log, what that question is asking you is what exponent is required to go from a base of b to reach the value of a. And I know that sounds crazy, but when you see the two forms next to each other, it might make a little bit more sense. This x is going to represent an exponent that you would give to the letter b, to this base here, and it will give you a. There are two forms that we deal with in math. You have exponential form and logarithmic form. That is because exponentials and logarithms, those two functions, are inverses of one another. They are opposite functions to each other. You might be able to see that from the graph here. These are exact opposites of what we saw when we had the graphs of exponentials in our last unit that started low. They had an asymptote going this way and up or down, whereas this asymptote is vertical here along the y-axis, and then it coats up. These are three different types of logs. This is the log of e. We will deal with that at a later date. Log base 10 and log base 2, just so you can see what the different functions look like when they are graphed. But hopping back up to the two forms up here at the top, like I mentioned, they are inverses of one another, so you can convert back and forth from something that is in exponential form into something that is in logarithmic form. Looking at logarithmic form over here really quick, we mentioned that the x from up here, our equals x, is the exponent that it takes the base to get to the answer. So over here in exponential form, it says that 2 to the third power is equal to 8. That's a fact. 2 times 2 times 2 is going to give you 8. A base to an exponent is going to give you an answer. The log is just asking you over here, this logarithmic form is saying, hey, I have a base 2 and I want to get to 8. What exponent, what does that equal? What exponent is going to get me there? So log base 2 of 8, remember we read it this way, base 2 of 8 is equal to x, which is equal to 3. 2 to what power? The third power is equal to 8. We're going to talk a little loop trick that will help you go back and forth from the two functions as we get into those things. You might have heard that from your Algebra 2 teachers last year. But log base 2 of 8 is equal to 3 because 2 to the third power is equal to 8. I've got the things here that match so you can see where the different parts go. and little keys down here for you to help remember what order they go in while you were looking at it. The base kind of goes in the basement. It is the lowest piece in the function, log base. So base 2, it's in the basement, it's the lowest part. It is written below the log. You can see it is kind of dropped down. Make sure you're being very careful when you're writing them that you don't put the 2 up here next to the 8 so it doesn't look like log of 28. Your answer, A for answer, goes next to B for base, and the two E's, equal and exponent, go next to each other. So your base is in the basement at the bottom, all of the B's, base, basement, bottom. A for answer, A goes next to B, and the two E's, equal and exponent, go next to each other. So we go back to, it was talking about what question is being asked. It's saying, hey, what exponent is required to go from this base to this answer? Well, to get from 2 times itself, how many times gives me 8? The answer to that is 3. But why logs? Why do we use them? What in the actual heck is the point of a log? Why do we have these? Well, we think as human beings in a logarithmic scale. I'm going to give you one example, and then I'll show you the example that's written down as well. It is the same thing that we say when we were kids, time went slower than it feels like it's going now. It feels like a year. As you guys get older, you may say that in a year it feels like it went by so fast. It's been almost a year now since we've been in some type of pandemic quarantine. Whereas when you were a child, the summertime between school break may have felt like an eternity. That is because we tend to think in logarithmic scales. This same thing happens when you're at the store. If you're at the store and you see that this store is selling this can of iced tea for $1, and the store down the street is selling that exact same can of iced tea, same size, same flavor, for $2, that seems like a big difference. Why am I going to pay $2 when I can pay $1 for it at the first store? From that $1 to $2 feels like a huge difference in price when you're talking about that can of iced tea. However, let's say that we're talking about a new piece of some kind of electronics, and I go to store A, and they're charging $100 for it. And I go to store B, and they're charging $101 for it. That does not sound like as big of a difference. That $101 is like, it's only $1 more, I'll just pick it up here. Whereas we were looking at those cans of iced tea, or that chocolate bar, a piece of candy, a bag of popcorn, if one store is charging $1 and another store is charging $2, it does seem like a much bigger difference than if we're looking at the difference between maybe $99 and $100, or $100 and $101. The linear difference of those two things is the same, like we just mentioned. Between the $1 and the $2, that's a dollar difference. Between $100 and $101, the difference there is both $1. However, the logarithmic difference, the log difference between $1 and $2 is 0.3. The logarithmic difference between $100 and $101 is 0.004. It is 4 thousandths compared to 4 tenths. It is 0.4% rather than 30%, if it's easier to look at in percentages. That kind of represents how we feel about these two things. 0.3 is a much bigger number than 0.004. Because the difference in our brains between that $1 and $2 bag of popcorn, or the $100 and $101 cell phone, does not feel as different because of the logarithmic differences. Logs are important because it's how we think. What I want you to do, just to kind of hit this home really quick, is put 0.3 in your calculator and hit enter. Add 0.3 again. Keep doing that until you reach 1. Did it take a long time? All right. What I want you to do now is take 0.004 in your calculator and hit enter. You probably see where this is going. Add 0.004 and keep going until you reach 1. How much longer did that take you? That difference that you feel, that's thinking with logs. That's thinking with logarithms. That's why we do this. That's the answer to, but why am I learning this? Miss Burke, why are you wasting my time? We think in logs. That is why we learn logs at this point in high school. Just to kind of hit that home between the two forms again, your top form is exponential form, and your bottom form here is in logarithmic form. They take the exact same components, just in a different order to kind of answer that question as to what exponent gives me this answer. So the log is asking, hey, I got a base and I got an answer. What exponent do I need to get there? Pause me here. Give these a good old college try. You're going to try answering first, kind of just identify the parts. What is your base? What is your answer? What is your exponent? You can use the little chart up at the top to keep you in check. And then convert it into the opposite form. So you have logarithmic form here, so we're going to write this in exponential form. You've got an exponential form here. Let's write it in logarithmic form. And this last one is in logarithmic form. We'll write it in exponential form. And there we go. The magic of the internet. These are your three pieces flopped over from exponential into logarithmic form and vice versa. Really quick, the last thing that I want to do with you guys is talk about what happens if your log is written without a base. If you see a logarithm and it does not have a base written there, it is assumed that that base number is 10. So you see here it just says log 10. Well, that means log base 10 of 10. Or if this one says log of 1/100th, that's log base 10 of 1/100th. Same with log 1000 is log base 10 of 1000.